Here we are again. Modern Automotive Technology by James E. Duffy. Lubrication System Fundamentals, Chapter 49. Objectives. After studying this chapter, you will be able to list the basic parts of a lubrication system, summarize the operation of a lubrication system, describe the construction of lubrication system parts, compare different lubrication system designs, explain the characteristics and ratings of engine oil, correctly answer ASE certification test questions that require a knowledge of lubrication system construction and operation. Technical terms: anti-friction bearing, bearing clearance, belt-driven oil pump, bio-based oil, cartridge oil filter, crankshaft-driven oil pump, dry sump, filter bypass valve, filter element, friction bearing, gear oil pump, gear-driven oil pump, multi-viscosity oil, oil additive, oil clearance, oil cooler, oil filter, oil gallery, oil pan baffle, oil pickup, oil pump, oil viscosity, oil weight, pickup screen, plain bearing, pressure fed oiling, rotary oil pump, scavenge pump, single viscosity oil, spin on oil filter, splash oiling, structural oil pan, sump, synthetic oil, vane oil pump, variable volume oil pump. The engine lubrication system forces engine oil to high friction points between metal contact surfaces in the engine to protect them from damage. Pressure oiling is critical to the engine's service life and dependability. Many high-performance gasoline engines and most diesel engines also have an oil cooling system to remove friction-generated heat from the lubricating oil. Without a lubrication system, friction between rapidly moving, heavily loaded parts would destroy an engine in a matter of minutes. Many engine parts would quickly overheat and score or partially melt from this friction. Engine bearings, piston rings, cylinder walls, and other parts could be ruined. Without circulating engine parts will lock up or weld together, and the crankshaft will no longer rotate freely. Some engines now have an integral oil/water/power steering combined into one large assembly. Therefore, it is critical that you understand the design and construction of engine lubrication systems. Lubrication system functions. Engine design and the properties of engine oil allow the lubrication system to accomplish the following functions: reduce friction and wear between moving parts, help transfer heat away from engine parts, clean the inside of the engine by removing contaminants, metal, dirt, plastic, rubber, and other particles, known contaminants. Cut power loss and increase fuel economy. Prevent internal engine parts from rusting and corroding. Absorb shocks between moving parts to quiet engine operation and increase engine life. I was getting a call, so I'm going to repeat some of the bullet points as I don't remember if I read them or not. Lubrication system functions. Cut power loss and increase fuel economy, prevent internal engine parts from rusting and corroding, absorb shocks between moving parts to quiet engine operation, and increase engine life. Basic lubrication system operation. When an engine is running, the oil pump pulls engine oil out of the oil pan. Before oil enters the pump, a screen on the pickup tube removes large particles from the oil. The oil pump then pushes the oil through the oil filter and oil galleries. The oil filter cleans the oil, removing very small particles. The filtered oil then flows to the camshaft, crankshaft, balancer shafts, lifters, rocker arms, and other moving parts. When oil leaks out of the engine bearings, it sprays on the outside of internal engine parts. For example, When oil leaks out of the connecting rod bearings, it sprays on the cylinder walls. This lubricates the piston rings, pistons, wrist pins, and cylinders. Oil is also pumped through the cylinder head gaskets to the valve train. Gravity causes the oil to flow back down into the oil pan for recirculation. Lubrication system components. A lubrication system consists of the following components: engine oil, oil pan and sump, oil pickup and screen, oil pump, pressure relief valve, oil filter, oil cooler, oil galleries, oil spray nozzles, oil pressure indicator, oil pressure gauge circuit. Engine oil. Engine oil, also called motor oil, is the lubricant for moving parts in an engine. It is needed to keep moving parts in an engine from making direct contact with each other. Its main purpose is to reduce friction. Engine oil is commonly refined from petroleum or crude oil. An oil film, or a thin layer of oil, separates engine parts to prevent metal-on-metal contact. Without the oil film, the parts would rub together and wear rapidly. As discussed previously, most engine oils are made by processing and refining crude oil. Engine oils are then mixed with oil additives. Synthetic oil. Synthetic oils are manufactured by further processing and blending crude mineral oils together with about 25% more synthesized or modified mineral oils. Synthetic oils can provide better performance in extreme cold than conventional motor oils because they contain engine protecting additives. Synthetic oils can also provide longer service life, less friction, and better fuel economy than conventional oil. However, synthetic oil typically costs more than regular motor oil. Bio-based oil. Bio-based oils, especially vegetable-based motor oils, are being developed as more environmentally friendly lubricating products. Experimentation with metal additives shows bio-based oils to be equal to crude or mineral oil in performance and superior in reducing carbon emissions. Oil additives. Oil additives increase the the protective properties of mineral, vegetable, or synthetic motor oil. After oil is refined, various chemicals are added to improve hot and cold characteristics. The following are common oil additives and their functions. Detergent/dispersants keep contaminants suspended in the oil until they can be trapped in the filter or removed when the oil is changed. Rust and corrosion inhibitors protect the metal engine parts by the formation of a barrier film between the parts and their environment. Foam depressants prevent oil foaming. Wear preventers are microscopic metal particles that are added to mineral oil to coat and seal metal surfaces. Pour point depressants improve low temperature fluidity. Phosphorus additives, in particular, are used as a cleaning agent in motor oil to carry oil impurities to the oil filter. Metal additives, such as zinc or titanium, are now added to motor oil to reduce part wear by coating internal engine parts with zinc or titanium film. Since metals have a high heat tolerance, metal additives aid in engine heat removal and burn resistance, and reduce carbon buildup on engine parts. The tiny metal particles coat the metal surfaces of engine parts with a film to limit surface wear. Oil clearance, or bearing clearance, is the small space between moving engine parts for the lubricating oil film. The clearance allows oil to enter the bearing to prevent part contact. For example, a connecting rod bearing typically has an oil clearance of about 0.002 inches, or 0.05 millimeters. This clearance is large enough to allow oil entry between the moving and the stationary parts of an engine. However, it is also small enough to keep the parts from hammering together and knocking during engine operation, or reciprocating action. The layer of oil inside the small bearing clearance acts as a hydraulic shock absorber. The thick oil cushions and quiets moving engine parts. Without oil filling the bearing clearance, a dry rod bearing will start knocking and damaging itself very quickly. Caution. If an engine is started without oil in its oil pan, the engine will start and run fine. However, after the oil is hammered out of the bearings, the engine connecting rods and crankshaft will hit metal on metal. The engine rods will start knocking loudly in a matter of seconds, signaling no oil pressure. This knocking can destroy connecting rod bearings in a matter of minutes. Engine bearings. The two basic types of engine bearings are friction bearings and anti-friction bearings. Each type can be used in many automotive assemblies besides engines. A friction bearing has two smooth surfaces that slide on each other. It is the most common type of bearing used in an engine. Crankshaft main bearings, connecting rod bearings, and cam bearings are normally friction bearings. They require a constant supply of pressurized oil. Friction bearings are also called plain bearings. An anti-friction bearing uses balls or rollers to prevent a sliding action between the bearing surfaces. Anti-friction bearings are only used in a few places in an engine. Roller lifters, for example, are engine anti-friction bearings. The roller cuts high friction and wear between the camshaft lobe and the bottom of the lifter. Anti-friction bearings do not require as much lubrication as friction bearings. Usually, splash oiling is sufficient. Oil viscosity is the thickness or fluidity, flowability of the engine oil. A high viscosity oil is very thick and resists flow. A low viscosity oil is thin and flows easily. Oil viscosity is also called oil weight. A viscosity numbering system is used to rate the thickness of engine oil. A high viscosity number indicates relatively thick oil. A lower viscosity number denotes a thinner oil. The oil's viscosity number is printed on the oil container. The SAE, or Society of Automotive Engineers, standardized this numbering system. For this reason, oil viscosity is written SAE 0, SAE 10, SAE 20, SAE 30, etc. Engine oil viscosity commonly ranges from a thin SAE 0 weight to a thick SAE 50 weight. Auto manufacturers recommend a specific SAE viscosity for oil used in their engines. Temperature effects on oil. Cold engine motor oil is very thick and resists flow. When heated, oil thins and becomes runny. This can pose a problem. The oil in a cold engine may be so thick that engine starting is difficult. The oil will not pump through the engine properly. This may increase starting motor drag and result in poor lubrication. As engine oil heats up, it tends to become thinner and less resistant to flow. If it becomes too hot and thin, the oil film can break down and part contact can result. It is important that the oil be thin enough for easy starting but thick enough to maintain lubrication when hot. Single viscosity and multi-viscosity oils. Single viscosity oil is rated and designed for a limited range of operating temperatures. Its viscosity is not as stable as multi-viscosity oils. Examples of single viscosity oils include SAE 20, SAE 30, and SAE 40 weight. Multi-viscosity oil will exhibit operating characteristics of a thin, light oil when cold and a thicker, heavier oil when hot. A multi-viscosity oil may be numbered SAE 10W30, 10W40, or 20W50. Multi-viscosity oil may be referred to as multi-weight oil. For example, a 10W30 weight oil will flow easily, like a 10 weight oil, when starting a cold engine. It will then act as a thicker oil, or 30 weight, when the engine warms to operating temperature. Use of this type of oil will help the engine start more easily in cold weather and provide adequate film strength or thickness when the engine is hot or at full operating temperature. Selecting oil viscosity. Normally, you should use the oil viscosity recommended by the automaker. However, in a worn, high-mileage engine, higher viscosity oil may be beneficial. Thicker oil tends to seal the rings and provide better bearing protection. It may also help reduce oil consumption, engine noise, and smoking. Tech tip. Never change a high-mileage engine over to full synthetic motor oil that does not contain metal additives. New synthetics that do not contain metal additives can actually wash old metal additives off metal surfaces, resulting in rapid part wear, especially at the camshaft lobes and piston rings. Engine oiling methods. There are two methods for lubricating engine components: pressure-fed oiling and splashing oiling. Pressure-fed oiling and splash oiling. Pressure-fed oiling is provided by the oil pump to the crankshaft bearings, camshaft bearings, lifters or cam followers, and rocker arm assemblies. This type of oiling is needed where load and friction are very high. Splash oiling occurs when oil sprays out and on moving parts to provide lubrication. This type of oiling is used between parts with moderate load. Splash oiling is used on many parts, including piston rings, cylinders, camshaft lobes, and timing chains. For an oil flow diagram. Okay, see figure 49-6 for an oil flow diagram. Okay, well, I try to skip those. Okay, it may also be referred to as oil throw-off. Oil pan and sump. SUMP. The oil pan is a reservoir or storage area for engine oil. The oil pan is normally made of thin sheet metal or aluminum. It bolts to the bottom of the engine block. The pan holds an extra supply of oil for the lubrication system. An oil pan drain plug allows removal of the old oil during oil changes. The oil pan gasket prevents oil leakage between the engine block and pan. The gasket has holes that line up with the oil pan's bolt holes. The oil pan bolts secure the pan to the engine block. Sometimes it's worded so weird. Okay. The sump is the lowest area in the oil pan. As oil drains out of the internal parts of the engine, it fills the sump. The oil pump can then pull oil out of the pan for recirculation. A sheet metal oil pan baffle may be used to keep the oil from splashing up on the spinning crankshaft. This keeps the crank from stirring air into the oil, causing oil foaming, and reduces a fractional horsepower loss. The baffle may be an integral part of the pan or a separate part installed above the pan. The pan, I was saying, reduces or eliminates completely oil foaming, which is very bad. A structural oil pan is designed to add strength to the engine bottom end and cylinder block. Most of these oil pans have thick ribs and bosses to help support the crankshaft and the main bearings. Structural oil pans can be made of thick aluminum or composite materials that are light yet strong. Dry sump lubrication system. A dry sump lubrication system uses two integral oil pumps and a separate oil reservoir for superior engine oiling. No oil is stored in the oil pan. The main oil pump draws oil from the reservoir and forces it to the engine bearings and other high friction points. A second oil pump, called a scavenge pump, pulls oil out of the pan and feeds it back into the reservoir. Dry sump lubrication systems are found on exotic high-performance cars. This design helps increase engine power and dependability because no oil remains in the oil pan to be splashed onto the crankshaft, pistons, and rods. Oil pickup and screen. The oil pickup is a tube extending from the oil pump to the bottom of the oil pan. One end of the pickup bolts and screws into the oil pump or to the engine block. The other end holds the pickup screen. The pickup screen, or strainer, is usually part of the pickup tube. Without the screen, the oil pump could be damaged by bits of valve stem seals and other debris flushed out of the engine. Oil pumps. The oil pump is the heart of the engine lubrication system. It forces oil out of the pan, through the filter and galleries, and to the engine bearings. The three basic types of engine oil pumps are rotary, gear, and vane. Rotary oil pump. A rotary oil pump uses a set of star-shaped rotors in a housing to pressurize the engine oil. As the oil pump shaft turns, the inner rotor causes the outer rotor to spin. The eccentric action of the two rotors forms pockets that change in size. A large pocket is formed on the inlet side of the pump. As the rotors turn, the oil-filled pocket becomes smaller as it nears the outlet of the pump. This squeezes the oil and makes it spurt out under pressure. As the pump spins, this action is repeatedly performed to produce a relatively smooth flow of oil. Gear oil pump. A gear oil pump uses a set of gears to produce lubrication system pressure. Oil drawn into the inlet side of the pump is caught in the gear teeth and carried around the outer wall inside the pump housing. When the oil reaches the outlet side of the pump, the gear teeth mesh and seal. Oil caught in each gear tooth is forced into the pocket at the pump outlet, and pressure is formed. Oil squirts out of the pump and to the engine bearings. Vane oil pump. A vane oil pump uses sliding wipers to build oil pressure. This is the newest oil pump design that provides for easy pressure and volume control. A variable volume oil pump is capable of building high oil pressure at idle and reducing pump volume per revolution at high engine speeds for better engine efficiency. These pumps help limit engine power losses while limiting the volume and pressure of the motor oil at high RPM. The hydraulic valves that operate a variable volume oil pump can also serve as a pressure relief valve. Oil pump drives. There are several methods used to drive an oil pump. A belt-driven oil pump uses a cogged belt running off the crankshaft pulley for power. This is commonly used in overhead cam engines using a timing belt. A gear-driven oil pump uses the engine timing gears for power. Some oil pumps are gear-driven off oil pan-mounted balancer shafts. This design can vary considerably from engine to engine. Gear-driven oil pumps are very dependable but costly to manufacture, making them rare. A crankshaft-driven oil pump is directly engaged to and powered by the crankshaft snout. The inner pumping element fits over and is keyed or locked to the crank snout. This type of oil pump drive is becoming more common because of its simplicity and dependability. I'm going to start reading the figure examples because they do actually have good information about, obviously they have good information, but I'm used to them just being like oh, this picture was taken by Adobe Photoshop shareholders and do not use it, and it's fair use, blah, 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 blah. But they actually do have some really nice information in these. So this is figure 49-10. In a variable volume oil pump, the oil pressure valve and spring normally hold the pump in the high volume per revolution position. When engine speed increases to try to reduce pressure, the hydraulic piston chamber on the outside of the pump housing is rotated to reduce pump volume per revolution at high engine speeds. These pumps help limit engine power losses while limiting the volume and pressure of the motor oil at high RPM. Crankshaft-driven oil pump. This oil pump is driven directly off the crankshaft snout. The drive spline on the crank turns the inner gear. The outer gear walks around to pump oil into the block. Okay. What's going on here? Hold on. Okay. This oil pump is belt driven. The pump bolts to the front of the engine. This type is common with overhead cam engines using a timing belt. Okay. Oil pressure relief valve. An oil pressure relief valve limits the pressure that can develop in the engine oil galleries. It is a spring-loaded bypass valve in the oil pump, engine block, or oil filter housing. The pressure relief valve consists of a small piston, spring, and cylinder. Under normal pressure conditions, the spring holds the relief valve closed. All the oil from the pump flows into the oil galleries and to the bearings. However, under abnormally high oil pressure conditions, cold, thick oil, for example, the pressure relief valve opens. Oil pressure pushes the small piston back in its cylinder by overcoming spring tension. This allows some oil to bypass the main oil galleries and pour back into the oil pan. Most of the oil still flows to the bearings, and a preset pressure is maintained. Some pressure relief valves are adjustable by turning a bolt or screw, or by changing spring shim thickness. The engine oil pressure setting can be altered. Oil filters. An oil filter strains impurities such as small metal, carbon, rust, and dirt particles from the circulating engine oil. It protects the moving engine parts from abrasive wear. Most oil filters screw onto the side of the engine. Oil filter types. There are two classifications of engine oil filters: spin-on filters and cartridge filters. The spin-on oil filter is a sealed unit. The filter element is permanently enclosed in the filter body. When a spin-on filter is serviced, a new filter is simply screwed into place. This is the most common type of oil filter. The cartridge oil filter has a separate element that fits in an engine-mounted housing. To service this type of filter, unscrew the cover from the top of the housing and remove the used filter element. Then, drop a new element inside the existing housing and replace the cover. A filter element is a paper or cotton filtering substance mounted inside the filter body. The element allows oil flow but blocks and traps small debris. A cartridge oil filter is sometimes used for heavy-duty or diesel applications and is the current trend for gasoline engines with high oil pressures. This description describes the construction of a pressure relief valve. A small piston or valve fits in a small cylinder. A spring holds the valve in a normally closed position. When oil pressure is too high, the spring compresses to open the valve. Excess oil bypasses the system and drains into the oil pan. This description has additional information for a cartridge oil filter. This oil filter normally mounts on one side of the engine block inside a cast aluminum filter housing. Oil filter condition is critical to the service life of the engine. This description has additional information about a spin-on filter. A spin-on filter is the most common oil filter type. An O-ring seal prevents leakage when screwed into its housing. The element traps debris and keeps it out of the engine. This description has additional or summary information for the cartridge type oil filter. The element is removed from the housing to change the filter. A filter bypass valve is commonly used to protect the engine from oil starvation if the filter element becomes clogged. The valve will open if too much pressure is formed in the filter. This allows unfiltered oil to flow to the engine bearings, preventing major part damage. Tech tip: the number one reason for premature engine failure is not changing the engine oil and filter at the recommended intervals. Decomposed oil results from excess heat and mechanical stress. The oil actually changes from a liquid to a solid, chocolate pudding-like substance. If you ever find extremely dirty or badly decomposed oil, warn the owner of the consequences of not changing the oil and filter at regular intervals. Oil filter housing. The oil filter housing is a metal part that bolts to the engine and provides a mounting place for the engine filter. The housing may also have a fitting for the oil pressure sending unit or sensor. A gasket normally fits between the engine and the oil filter housing to prevent leakage. Sometimes the pressure relief valve, filter bypass valve, and oil pump are housed inside the aluminum casing. The oil filter housing often bolts to the side of the engine block. Figure 49-18. In this setup, the oil pressure sending unit is mounted in the filter housing. Note the small oil cooler adapter that mounts between the filter and the housing. Hoses run between the adapter and an oil cooler. Oil cooler. An oil cooler may be used to help lower and control the operating temperature of the engine oil. It is a heat exchanger or radiator-like device connected to the lubrication system. Oil is pumped through the cooler for the heat removal. Heat is removed by air flowing through the cooling fins before the oil flows back into the engine. Oil coolers are frequently used on turbocharged engines or heavy-duty applications, such as trailer towing packages. Oil galleries. Oil galleries are passages through the cylinder block and head for lubricating oil. They are cast or machined passages that allow oil to flow to the engine bearings and other moving parts. The main oil galleries are large passages through the center or side of the cylinder block casting. Small passages feed oil to the crankshaft bearings, rod bearings, camshaft bearings, and valve train. The main galleries also feed oil to small passages running up through the cylinder block and into the cylinder heads. This description has new information or summarized information about oil coolers. Figure 49-19. Oil coolers allow transfer of heat out of the oil and into the surrounding air, like a cooling system radiator. They are used for high performance or heavy duty applications. High pressure lines and hoses carry oil to and from the cooler. This description has new information or summarized information about oil galleries. Figure 49-20. Oil galleries allow oil to pass through the engine. The main galleries are the larger passages in the block. Note how oil flows through the hollow push rods to the rockers. Oil spray nozzles. Oil spray nozzles direct a stream of engine oil into the bottoms of the engine pistons, timing gears or chain, and other moving engine parts. The extra oil provides added lubrication and helps carry heat away from the parts. Oil pressure indicator. An oil pressure indicator warns the driver of a low oil pressure problem. The ECM circuit activates a warning light in the vehicle's dash. An oil pressure switch is opened and closed by oil pressure so that it can operate the dash indicator light. It screws into the engine and is exposed to one of the oil galleries. When oil pressure is low, the engine is off or has a mechanical problem. The spring in the sending unit holds a pair of contacts closed. This completes the circuit. and the indicator light glows. When oil pressure is normal, the oil pressure acts on a diaphragm in the sending unit. Diaphragm deflection opens the contact points to break the circuit. This causes the warning light to go out or remain off. Oil pressure gauge circuit. An oil pressure sending unit operates the oil pressure gauge and the warning light. The sending unit uses a variable resistor instead of the contact points. As more oil pressure is developed, the sending unit diaphragm is deflected a proportional amount. This causes an equal amount of sending unit resistance change. Low oil pressure causes low sending unit resistance. High current flow and low oil pressure gauge readings. What the fuck? Oh my gosh, I'm reading weird. Okay. Low oil pressure causes low sending unit resistance. High current flow and low oil pressure gauge readings. High oil pressure causes high resistance in the sending unit to allow low current flow for deflecting the pressure gauge needle to the right. This description has additional information or summarized information of the oil spray nozzle, figure 49-21. The oil spray nozzle squirts engine oil onto the bottom of the piston to cool the piston head and add lubrication for the wrist pin. A pressure valve in this nozzle opens only when a specific oil pressure is reached. Tech tip: an engine oil pressure must be very low, under about 10 psi at idle, before many low oil pressure warning lights will go on. Light engine bearing knock or lifter noise will often result before the warning light is energized. If oil pressure drops low only at idle, excessive rod and main bearing clearances are indicated. Loose engine bearings are allowing too much oil flow through the bearings, which lowers engine oil pressure at low RPM. Oil level sensor. Some cars are equipped with an oil level indicator that registers the actual quantity of oil in the engine. It is similar in operation to the oil pressure indicator light. An oil level sensor is used to warn the driver to add oil to the engine. The sensor is usually mounted on the oil pan and can be a float variable resistance type or an optical type sensor. Low oil pressure safety circuit. A low oil pressure safety circuit can be used to shut off the engine if oil pressure drops too low. This will protect the engine from major damage in case of a lubrication system failure or loss of oil pressure. The circuit usually disables the ignition system to keep the engine from starting or running. The oil pressure switch or sending unit is wired to the engine control module. If the ECM detects a dangerously low oil pressure, it disables the engine ignition system. This prevents engine damage by preventing the driver from operating the vehicle without oil pressure. This description has additional or summarized information about low oil level sending unit. Figure 49-22. This low oil level sending unit uses a float and switch to operate a dash indicator. If the oil level becomes low from leakage or consumption, the float drops to close the switch and turn the dash light on. The driver then knows to add oil before the level is low enough to cause damage. Summary of Chapter 49, Lubrication System Fundamentals. The lubrication system forces oil to high friction points in the engine to protect moving parts from friction, wear, and damage. Engine oil is needed to keep moving parts in an engine from making direct contact. A friction bearing has two smooth surfaces sliding on each other. An anti-friction bearing uses balls or rollers to prevent a sliding action between the bearing surfaces. Oil viscosity is the thickness or fluidity or flowability of the engine oil. Multi-viscosity oil will exhibit operating characteristics of a thin, light oil when cold and a thicker, heavier oil when hot. An oil service rating is a set of letters printed on the oil bottle to denote how well the oil will perform under operating conditions. The oil pickup is a tube extending from the oil pump to the bottom of the oil pan. The oil pump is the heart of the engine lubrication system. It forces oil out of the pan, through the engine filter, galleries, and to the engine bearings. A pressure relief valve limits maximum oil pressure. It is a spring-loaded bypass valve in the oil pump, engine block, or oil filter housing. An oil filter removes small metal, carbon, rust, and dirt particles from the engine oil. It protects the moving engine parts from abrasive wear. Oil galleries are small passages through the cylinder block and head for lubricating oil. An oil pressure switch is opened and closed by oil pressure so that it can operate the dash oil pressure indicator light. An oil pressure sending unit uses a variable resistor to operate the oil pressure gauge and the warning light. This has been chapter 49 of Modern Automotive Technology by James E. Duffy. Lubrication System Fundamentals. I hope you have enjoyed this audio. I hope it has benefited you in some way. This has been your narrator, Joseph Cuevas, and I hope to see you guys very, very soon. Have a fantastic day.